Hello, and this time resistors in parallel. The problem here is we've got two resistors wired up like this. They are in parallel only if one side of them is connected together and the other side of them are connected together. Both sides of both resistors have to be connected together for them to count as in parallel. Right. Now, in this situation, we've got the same voltage across each of the resistors. V, this difference in voltage between X and Y, appears across both of the resistors. So if we were going to apply Ohm's law to each of these two resistors, which we are, it would be the same voltage in both cases, but different currents, because the resistors have different values. So, let's apply Ohm's law to this situation and see if we can produce something of the form total voltage from X to Y equals total current flowing from X to Y times an effective resistance which behaves the same as these two resistors in parallel. Let's do some analysis. Okay, let's have a look. We've got our total voltage across both resistors is V. So Ohm's law applied to R1 would say that V equals I1, the current through R1, times R1. And applying Ohm's law to R2 would give us that the same V equals I2 times R2. Now, applying Kirchhoff's current law to this node in the circuit here, we can see that I1 plus I2 must equal I, the total current flowing out of this network. So we have the total current I equals I1 plus I2. So I is, substitute in from here, V over R1, plus I2, substitute in from here, V over R2. Extract the factor of V out of both of those, and we end up with this. Right, all we now need to do is to divide both sides of the equation by this, and we end up with this. V equals I divided by 1 over R1 plus 1 over R2, which I might write as I times 1 over R1 plus 1 over R2 inversed. I compare that to the form of Ohm's law, the total voltage difference across the network equals the total current flowing into or out of the network multiplied by the effective resistance of the network. Compare this formula to this formula. Well, the voltage difference is just what's labelled V in the diagram. The current, well, I is the total current flowing out of the network. Therefore, the equivalent resistance must be given by this formula here. We have Req, the effective resistance, or equivalent resistance, is 1 over R1 plus 1 over R2. You can multiply up that top and bottom by R1 times R2 and get the formula R1 R2 over R1 plus R2, which is often easier to work with. It's the product of the resistors divided by the sum of the resistors, although, as we'll see, this only works if you've only got two resistors. If you have three resistors in parallel, you can no longer use this formula. It's just another form of the formula when you have two resistors in parallel. What happens if you have three in parallel? Well, pretty much the same idea. We just have another current. We have an I3 that flows through R3, which means that our total current I is now the sum of three currents. And that means that if I substitute in this for this, if I substitute this function into here, I'd get another term, V over R3, in this equation here, which would lead to another term, 1 over R3, in this equation here. Following that through, and I would end up with the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. Sometimes people write this as 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus and so on. That's fine too. Any one of these forms will work fine, except that one, which only works when you've got two resistors in parallel. Right. Does it work? Once again, we can go and have a look at the simulator and see what it does. Right, here we've got two resistors in parallel, because you can tell they're in parallel because both ends of the resistors are connected together. And we have another resistor here, which is just a single 500 ohm resistor. Now, the current through the 500 ohm resistor is, let's put this in the middle so we get a nice round number. The current through the 500 ohm resistor is 10 milliamps. 5 volts divided by 500 ohms is 0.01 or 10 milliamps. The current through the 1K resistor will be 5 milliamps, because we got 5 volts across a 1K resistor. So the current through this resistor is 5 divided by 1000 or 5 milli. And equally, we have 5 milliamps through this resistor as well. Both of those currents then join together, which means the current flowing down this wire is 5 plus 5 or 10 milliamps. We can check that. We can just stick in an ammeter into the wire here, and it says 10 milliamps, as expected. So the total current flowing through the network of these two resistors is equal to the total current flowing through this resistor. And the same voltage appears across them. So, yes, this 500 ohm resistor behaves the same way as these two 1K resistors in parallel. And that's exactly what the formula would predict. If we have a look at putting some numbers in, 1 over 1K plus 1 over 1K is 2 over 1K, or 1 over 500. So, the equivalent resistance of two 1K resistors in parallel is 1 over this, which is 1 over that, which is 1 over 500. That's just equal to 500. It's worth noting some special cases here. If you do have two resistors that are equal, and you put them in parallel, then the result is half of the resistances of either of the individual ones. We could use this formula up here to prove that as well. If the resistance was X, say, then the equivalent resistance, X times X all over X plus X, gives you X squared over 2X, and that's just X over 2. The equivalent resistance is half of the individual resistors. That's worth knowing as well. Right, I think that's all we need to know about resistors in parallel. Next, we'll look at some examples of a few more complex types of resistor networks.